the enigmatic planet hiding between Mars and Jupiter, creating the asteroid belt. The main asteroid belt, as you know, is an orbital region located between Mars and Jupiter. It spans at least 300 million kilometers in width and is packed with billions of objects, ranging in size from pebbles to continents like Australia. But has it always been this way? Is there any truth to the theory that once upon a time a single large planet orbited in this region before it disappeared, leaving behind this vast herd of cosmic bison? To understand this, we need to blend together a variety of elements, such as dreams, hopes, human stories, and scientific tales. Raise your hand if you've ever dabbled in astronomy and haven't at least once heard of the Titius-Bode Law. Almost every astronomy book, when introducing the basics of our planetary system, mentions this simple numerical sequence, often as a mathematical curiosity, that surprisingly fits the planetary distances in the solar system with a few exceptions. It's an easy rule to remember and doesn't require any special mathematical knowledge to apply, which explains its widespread popularity. The idea that a mathematical law could describe the motion of celestial bodies, including planetary distances, dates back to ancient times. It was supported by philosophical thought, which saw nature as the ultimate expression of order, and religious thought, which could only conceive the Creator's marvelous work in terms of absolute and rigorous precision. The term Titius-Bode Law refers to an empirical relationship that approximately defines the average distances of planets from the Sun in astronomical units, AU. Although it was discovered in 1741 by German astronomer Wolf and rediscovered by his compatriot Johann Titus in 1772, it is best known for Johann Bode's work in popularizing it. In 1778, Bode also provided a precise mathematical formulation. According to this law, the distances of the planets from the Sun in AU originate from the series 0, 3, 6, 12, 24, 48, 96, where each number starting from the third is double the previous one. Adding 4 to each number and dividing the result by 10 gives the following values: 0.4, 0.7, 1, 1.6, 2.8, 5.2, 10, which from Mercury to Saturn represented the actual distances of the known planets with great accuracy. It's worth noting that Bode's more prominent position soon led to the relationship being associated solely with his name, often forgetting Titus's contribution. Despite Bode acknowledging his colleague's work in later editions of his publication, the theft had already occurred, a clear example of how even scientists are not immune to committing injustices. Beyond this, the law became part of established knowledge, although the value of 2.8 remained unexplained as it did not correspond to the distance of any known planet at the time. Just a decade later, a sensational event helped convince even the few who still considered it merely a fun mnemonic device. On March 13, 1781, Anglo-German astronomer William Herschel discovered a new planet, the first since those known since antiquity. Uranus, as the new arrival was named after a political scientific debate that lasted several years, joined the family of the Sun. But the surprise was double. After the initial calculations, it was astonishing to find that the distance of the new celestial body almost perfectly matched the sixth position in the sequence of planetary distances, with a predicted distance of 19.6. The average distance from the Sun turned out to be 19.2 astronomical units. At that point, as you can imagine, a mad rush began across Europe to discover the planet that surely, given the recent confirmation of the relationship's reliability, had to be located between Mars and Jupiter at the predicted distance of 2.8 AU. For many years, despite the efforts of numerous observers, there was no trace of the missing planet. Could it be that a mathematical relationship so precise in all other cases could disappoint the scientific community's expectations so greatly? Doubts began to arise, until a passionate and wealthy Hungarian baron, Franz Xaver von Zach, decided to take matters into his own hands. In 1800, he founded the United Astronomical Society, composed of 25 of Europe's best observers, including Maskelyne, William Herschel, Charles Messier and Heinrich Olbers. This group, dedicated to bringing order to the unruly solar system, became universally known as the Celestial Police. With absolute systematicity, each observer was assigned a 15-degree slice of the ecliptic to search for the missing planet in that region. But as often happens, the race was won by someone who wasn't even participating, the Italian Giuseppe Piazzi. Giuseppe Piazzi, a priest and director of the Palermo Observatory, wasn't looking for a planet. He was simply checking the position of an already cataloged star when, on the first day of the 19th century, January 1st, 1801, he saw another point of light near the star he was observing, not marked in existing star catalogs. Continuing to observe the intruder, he noticed it was moving. Hey guys, just a moment before we continue. Be sure to join the Insane Curiosity channel. Click on the bell, you'll help us to make products of even higher quality. After a series of setbacks, including losing sight of the point of light due to bad weather that prevented observations for 2 weeks, it was finally rediscovered. Calculations confirmed it was indeed the missing planet they were searching for, located at the distance predicted by the law. Piazzi named the new planet Ceres after the Roman goddess of harvest and the protector of Sicily. This was the peak of scientific recognition for the Titius-Bode Law. But good things don't last long. A first doubt about the true nature of Ceres arose on March 28, 1802, when Heinrich William Olbers, a member of the Celestial Police, found a second planet named Pallas at the same orbital distance. What was happening? 2 planets at the same distance from the Sun? How many more could there be? Would this oddity change the law? An answer came quickly from Herschel, who on May 13, 1802, communicated to the Royal Society his intention not to consider the 2 newly discovered objects, Ceres and Pallas, as planets, but simply as asteroids, because through the telescope, no matter how much they were magnified, they stubbornly maintain a stellar point-like appearance. Herschel's decision irritated Piazzi, but it also provoked a reaction from Olbers, who on June 17th wrote a letter to Herschel expressing his thoughts. Excuse me for not responding in English. I can read and understand your language, but writing it is difficult for me. I also think that Ceres and Pallas are very small, but as small as you, honored sir, have found them to be, I could have never imagined. I'm curious to know how you managed to measure the apparent diameters of these small bodies. Honestly, I can't understand it. I agree with you, sir, that Ceres and Pallas differ in many ways from the other planets, and the name asteroids you proposed seems to me to describe the nature of these objects very well. The similarity in their revolution periods, average distances, and the remarkable proximity of their orbits to each other suggested an idea to me, which I would not yet call a hypothesis, on which I would like to know your opinion. Could it be that Ceres and Pallas are just fragments of a large planet that once occupied that space between Mars and Jupiter, similar in size to all the others, and that millions of years ago, as a result of a comet impact or an internal explosion, disintegrated? Thus, Olbers expressed for the first time, along with his resentment, his idea about the origin of the 2 asteroids discovered so far. To confirm this, the German astronomer spent the rest of his years searching for other fragments, and especially for a key that would allow him to find others almost for sure waiting for them at a well-defined point in their orbit. The system he devised was based precisely on his hypothesis of the disintegrated planet, from which fragments must have originated, following orbits somehow dramatically linked. If this was indeed the case, Olbers thought then there must be 2 points where these orbits intersect, and it is precisely around these nodes that telescopes should be pointed. Apart from the partial inaccuracy of the assumption, the orbits followed by the fragments of an object subjected to a destructive impact share only one orbital point, the one from which the dispersion originates. There remained a significant problem to overcome. Where were the 2 nodes? Olbers believed he had found the answer shortly after his discovery of Pallas. That asteroid was found about a half a degree away from the position where Baron von Zach had rediscovered Ceres on December 31st, 1801, after it had been lost for a long period. This convinced the German astronomer that one of the nodes was located precisely in that region, the northern part of Virgo. Whether his hypothesis was reckless or not, after years of continuous research, on March 29, 1807, Olbers managed to find another small planet, which would later be called Vesta, located incredibly less than a degree from the other two. Can you grasp the absurdity of this? The entire celestial sphere is composed of about 40,000 square degrees, and 3 discoveries of large asteroids occurred in the same square degree. Truly unbelievable. The whole thing, as you can imagine, drove the entire astronomical community of the time crazy. Almost everyone enthusiastically embraced Olbers' hypothesis. A planet orbiting between Mars and Jupiter must have existed in primordial times and then catastrophically exploded for unknown reasons, leaving only a multitude of small orbiting fragments in its place. This narrative became popular in both scientific and popular circles, and the hypothetical planet became a fact in books. In 1823, German writer Johann Gottlieb Radloff proposed naming the destroyed planet Phaeton, linking it to the myth of Apollo's son, struck by Zeus's lightning and falling to Earth for clumsily driving the solar chariot, usually driven by his father Apollo. And so it was. The idea that something as large as a planet could be destroyed both horrified and fascinated the public, especially in the mid-20th century, when the world was under the nightmare of global destruction by nuclear weapons. It instilled in humanity a deep aversion to all scientific research capable of unleashing uncontrollable energy processes. Theories regarding the formation of the asteroid belt due to the explosion of a hypothetical fifth planet are collectively called the destruction theory. Each one attempts to explain how a planet, imagined to be at least as large as Mars, could have disintegrated. What actually happened? Perhaps a close encounter with Jupiter that tore it apart with its tidal forces. A collision with a large comet? An explosion triggered by the instability of its core? Before answering these questions, be sure to stay tuned afterwards if you haven't seen our earlier release on the Goblin, a planet that is leading us to mysterious Planet 9. The attempt to explain the inexplicable lasted almost until our time, and the last picturesque hypothesis was presented in 1953 by Soviet-Russian astronomer Ivan Ivankovich Putulin. He suggested that Phaeton was destroyed due to its enormous centrifugal force, subjected to a rotation period of only 2.6 hours, applied to a diameter of 6,800 kilometers. In the end, the planet was so distorted that it projected its equatorial region outward, and the instant exposure of the core did the rest, leading to a total fragmentation. All romantic and fascinating hypotheses, but none able to withstand the test of time. Today, many clues suggest that Olbers' theory lacks any foundation. For one, all known asteroids combined would form a very small mass, much less than that of Pluto, Mercury, and even the Moon. Additionally, analyses of meteorites that have landed on Earth, essentially fragments of asteroids that reach the ground, show that the material they are made of has never experienced the pressures and temperatures found inside a planet. Nowadays, it's believed that asteroids are the result of a planetary abortion, meaning they are planetesimals that couldn't form a planet in this region due to the gravitational disturbance from Jupiter. This disturbance was strong enough to perturb their orbits and mix them up, creating numerous collision paths among these small bodies. Mutual collisions would have fragmented the planetesimals into smaller and more numerous bodies, leading to the current situation where impacts have drastically decreased. This idea seems confirmed by the presence of clusters of true asteroid families in certain favored orbits and the almost total absence in others, known as the Kirkwood gaps, which are evidently disfavored by Jupiter's perturbations on the orbital motion of these small bodies. But folks, by now you should understand how science works. Even this, until we find a way to prove it, must be considered just a theory. And the way to do that is to closely study extrasolar planetary systems to see if asteroid belts have formed there as well. And I want to be optimistic, especially with the upcoming operation of the 39-meter telescope being built in the Atacama Desert in Chile. Within 10 years, we will know the truth. There was a time when astronomers were fascinated by the possible existence of a so-called Planet X, believed to be responsible for the supposed irregularities observed in Neptune's orbit. the eighth and most distant planet in the solar system. After years of persistent search campaigns, Planet X was finally found in February of 1930. The X here, note, was not meant as the Roman numeral for 10, but rather as an unknown variable. The new arrival, which became the ninth planet in the solar system, was named Pluto. Soon after, based on further supposed irregularities in the motions of known planets, the search for a 10th planet began. This search remained fruitless until today, and in 2006, after Pluto's reclassification, it was renamed and continued as the search for the ninth planet, or again Planet X, with one small but significant difference. This time, the possible existence of a planet much farther than Neptune wasn't based on tiny irregularities in the orbital motions of nearby planets, but on the confirmed existence of a group of small trans-Neptunian objects, or TNOs, that all seem to move in very peculiar orbits. This suggests that there must be some hidden mass somewhere capable of altering all their orbits in the same way. Among these very special TNOs, called Sednoids, after their largest and most famous representative, Sedna, is the Goblin, which, when discovered in 2015, earned the title of the solar system object with the most distant aphelion. Finding something without knowing exactly where to look is no easy task, and if it's not even certain that the thing exists, it becomes even more complicated. Michael Brown and Konstantin Batygin know this well. These two astronomers are quite convinced that a planet at least twice the diameter of Earth is orbiting in the far reaches of our solar system, unseen by anyone. For years, these two persistent scientists have argued that the existence of this ninth planet would help explain the strange similarities in the orbits of some objects in the most remote parts of our solar system. So far, it's been all about theories and celestial dynamics models, discussed by an astronomical community equally divided between enthusiasm and skepticism. For quite some time, studies supporting and opposing the existence of this planet have alternated. The most recent study, published just a few weeks ago, suggests that Brown and Batygin's ambitious hypothesis rests on a misunderstanding of a simple statistical error. To fully understand the issue, we need to take a long step back in time when the Kuiper Belt was still unknown. As we mentioned earlier, on February 18, 1930, the world learned of the discovery of what was then considered the ninth planet of the solar system, painstakingly searched for by the young Clyde Tombaugh and finally found on photographic plates taken with the 13-inch astrograph at the Lowell Observatory in Flagstaff, Arizona. After that monumental discovery, no one searched for other objects orbiting beyond those remote distances for a long time. Almost no one believed there was anything else to find, as the planet discovered by Clyde Tombaugh seemed to account for the supposed irregularities observed in the movements of Uranus and Neptune. Over the years, however, it became increasingly clear that Pluto was not the massive planet it was thought to be, and the idea began to take hold that beyond 40 astronomical units, the solar system hid much more than we could see. In 1992, a group of researchers led by American astronomer Chad Trujillo announced the discovery of the first trans-Neptunian asteroid, thus proving the existence of a second asteroid belt, 15 times farther away than the one we know between Mars and Jupiter. This region extends beyond Pluto for billions of kilometers and was named the Kuiper Belt in honor of Gerard Kuiper, the Dutch astronomer who theorized its existence in the 1950s. Observations and discoveries that followed led astronomers over the years to estimate that this enormous reservoir of icy worlds could contain hundreds of thousands of objects, some even hundreds of kilometers in size. Pluto was not just an exception. There was much more out there at the edges of our solar system. It just needed to be found. Taking up the challenge in the early years of this century was primarily Caltech astronomer Michael Brown, who quickly discovered in that area objects as large as Quaoar, Sedna, Orcus, Makemake, Haumea, Gonggong, all planetoids with diameters between 1,000 and 2,000 kilometers. This string of successes culminated in 2003 with the discovery of Eris, a planet the same size as Pluto. Ironically, it was this very crowding of planets that led to the 2006 reclassification of Pluto and Eris as dwarf planets. The decision, as you might recall, came after a turbulent debate, with Brown himself surprisingly at the forefront, advocating for the need to redefine the very concept of a planet. This move not only demoted Pluto, but also his own discovery, Eris. Since 2006, little else has been discovered in the Kuiper Belt. Many objects with diameters around hundreds of kilometers, but none of semi-planetary size. Astronomers' work began to shift towards a statistical analysis of the various populations of objects in the belt. Then, on January 20th, 2016, Brown, along with his postdoc student Konstantin Batygin, published a paper in the Astronomical Journal titled Evidence for a Distant Giant Planet in the Solar System. In their study, Batygin and Brown analyzed the orbital data of Sedna and a group of 5 other objects, noting that the major axes of their orbits are almost aligned in the same direction, and, more importantly, that their orbits all have very similar inclinations. The strangest and most mysterious of these objects turned out to be a slowly moving dot, which the discoverers, with Halloween approaching, quickly named the Goblin. This large asteroid moves into the inner part of the Oort cloud, taking no less than 32,000 years to complete an orbit around the Sun. On October 13, 2015, the Goblin was spotted by the Subaru telescope in Hawaii, the Magellan telescope in Chile, and the Discovery Channel telescope in Arizona almost by chance, a collateral sighting during the hunt for Planet 9. At the time of its discovery, the Goblin had a magnitude of plus 24, about 9 million times fainter than the stars just visible to the naked eye, and was about 80 AU from Earth, roughly 15 AU from its perihelion. Assuming an albedo of 0.15, meaning the celestial body reflects 15% of the solar radiation, it is expected to have a diameter of about 300 kilometers. This makes it much smaller than Pluto or even Sedna. If Sedna impressed astronomers with its highly elliptical orbit, ranging from a minimum distance of 76 astronomical units from the Sun to a maximum of nearly 1,000 AU, the Goblin astonishes everyone with a perihelion of 65 AU and an aphelion of a staggering 2,155 AU, equivalent to 323 billion kilometers, about 200 billion miles. It took years to learn enough about it and its orbit, but it seems to have been worth it because the data aligns with those of other small planets observed previously and fits perfectly with the theory of a supermassive planet X, whose gravity influences the orbits of smaller celestial bodies. To better understand these distances, remember that bodies in the Kuiper Belt, including Pluto, are all trans-Neptunian objects, with average distances from the Sun between 30 and 55 AU. However, the 6 objects studied by Batygin and Brown do not belong to the Kuiper Belt. They are classified as ETNOs, extreme trans-Neptunian objects, because they have extremely elongated orbits. Among these are 4 so-called sednoids, objects with a perihelion so high that it keeps them far enough to avoid significant gravitational perturbations from Neptune. Among them is the Goblin. While studying the orbits of these 6 ETNOs, Batygin and Brown noticed something strange. A characteristic of their orbits called the argument of perihelion, essentially the angular orientation of the orbit's major axis, was similar in all 6 bodies. Additionally, the inclination of their orbital planes was also very similar. In short, there was something, a force that seemed to be acting on the orbits of the 6 ETNOs, aligning and elongating them all in the same way. These 6 bodies, moreover, were discovered by 6 different telescopes during as many different surveys, ruling out the hypothesis that their grouping around the Sun was due to an observational bias. The 2 astronomers calculated that there was only a 0.007% chance that this orbital arrangement was random, and after conducting a series of simulations based on various types of gravitational interactions, they became convinced that the most likely cause of the orbital similarity of the 6 ETNOs could only be the gravitational pull exerted on these bodies by a ninth planet in the solar system far from the Sun. Their simulations indicated that a planet with a mass about 10 times that of Earth, moving along a highly elongated orbit averaging 700 AU, with a perihelion of 200 AU and an aphelion of 1200 AU, situated in an elliptical orbit with an eccentricity of about 0.6, a semi-major axis of 700 astronomical units, perihelion and aphelion at 200 and 1200 astronomical units from the Sun respectively, and an argument of perihelion opposite by 180 degrees to that of the 6 ETNOs, could perfectly explain the orbital confinement of these 6 small planets. After the publication of their study, debates about the existence of the hypothetical planet 9 flourished, but so did the search for it. However, this search was conducted almost blindly. If this distant and cold body truly existed, it would have an apparent magnitude greater than 22, meaning that astronomers would need to detect the movement of a light point at least 600 times fainter than Pluto. Over the years, thanks to increasingly powerful and precise telescopes, astronomers have become quite adept at searching for specific categories of celestial bodies. They specify the desired characteristics to the instruments to exclude everything else from the field of view and then reevaluate the results. In a sense, though, it's like trawling, whereas in the case of the 9th planet, a harpoon would be needed. There aren't many telescopes powerful enough for this purpose, and they are in high demand by researchers. Finding available slots is difficult, and astronomers often end up with just a couple of nights a year to carry out their observations. In 2019, a further study by Brown and Badigan increased the number of ETNOs with apparently aligned orbits to 14. This allowed the authors to refine their estimates of the characteristics of the hypothetical planet 9. The average distance from the Sun, 400 to 500 AU. Perihelion distance, 280 AU. Aphelion distance, 650 AU. Diameter, 25,000 kilometers. Mass, 5 times that of Earth. Orbital inclination, 20 degrees. Although the evidence presented by Badigan and Brown seems quite convincing, no one really knows if Planet 9 exists or not. And until we discover it through direct observation, its existence won't be scientifically confirmed. But where could it be right now? For now, no one really knows, although the studies conducted so far provide a rough idea of its motion in the sky and its brightness. Current scientific efforts are focused on narrowing down the search area. For example, new simulations by Badigan and Brown have reduced the possible location of Planet 9 to an area of about 600 square degrees. Remember, the entire celestial sphere is about 40,000 square degrees. Excluding areas of the sky already monitored by automated surveys like Pan-STARRS and WISE, the most reasonable conclusion is that Planet 9 could be near its aphelion, about 600 AU away. Statistically, an object in orbit around this star spends much more time near its aphelion, where its speed is lower. Even if Planet 9 were real and large, it would be incredibly faint at its predicted distance from the Sun. You might think that if it were 10 times farther than Uranus and almost the same size, it should be only 100 times fainter, as brightness decreases by 1 over the square of the distance. But sunlight suffers from this problem twice from our perspective. The sunlight reaching such a distant world would be 100 times fainter than the sunlight reaching a closer world, but then that light is reflected and has to travel 10 times farther before reaching Earth again. Instead of decreasing by 1 divided by r to the power of 2, the light we actually see decreases by 1 divided by r to the power of 4, making any world that distant incredibly difficult to see. Very faint objects can be detected with dedicated astronomical surveys, but finding an object that doesn't shine with its own light, like a star, but with reflected light, is made even more difficult by the problem of reflected sunlight. For an object twice as far away as another, the light must first travel twice the distance, meaning only 1/4 of the light reaches it, and then travel back twice the distance, resulting in 1/16 of the original brightness. The 1 divided by r to the power of 4 relationship for brightness distance in this case is catastrophic. Its magnitude would then be a plus 22, a brightness within the reach of any professional telescope, but unfortunately in the direction of the center of the Milky Way. And if this rough prediction were true, discovering Planet 9 could be extremely complicated against the incredibly dense star fields near the center of our galaxy. In short, the scientific debate over the existence of the 9th planet continues, with its ups and downs. This debate, sometimes marked by very polemical attacks, was reignited a year ago by a new study titled "No Evidence for Orbital Clustering in the Extreme Trans-Neptunian Objects." According to the authors of the study, led by Kevin Napier from the University of Michigan, there is nothing particularly strange about the orbits of the 14 ETNOs cited by Brown and Badigan, and their similarity could be just the result of a statistical fluke. Their thesis is that since these objects are few, small, faint, very dark, and difficult to spot except on rare, fortuitous occasions, the apparent clustering in a particular region of the sky could be a function of the characteristics of the telescopic survey that identified them, rather than the presence of a great attractor. It cannot be ruled out that their distribution is actually uniform across the celestial sphere, which would negate the need to invoke the existence of a perturbing planet. Of course, Brown and Badigan do not share this opinion. Their polemical streak is evident in Badigan's response. "I'm still quite optimistic about Planet 9. If you see a bunch of bears to the east, you might think there was a bear cave there. But Napier is saying the bears are all around us because we haven't checked everywhere. That logical jump is not one you can make." To untangle this issue, further observations are needed to identify an increasing number of trans-Neptunian objects to determine once and for all whether the clustering that led to the hypothesis of Planet 9 exists or not. The 9th planet will continue to keep astronomers busy for a long time, but new data to resolve their dispute could arrive within a few years. Since the planet is expected to be moving in the northern celestial hemisphere, the primary search is currently being conducted with the Subaru telescope on Mauna Kea, Hawaii, which has both a large enough aperture to see faint objects and a wide field of view to shorten search times. In Chile, the Vera Rubin Observatory is under construction, equipped with a powerful telescope, large synoptic survey telescope, that will conduct observational campaigns to photograph the night sky of the southern hemisphere. It will allow precise mapping of Kuiper Belt objects and will likely lead to the discovery of many more trans-Neptunian objects. The American astronomer Vera Rubin, after whom the new telescope is named, was a pioneer in the study of galaxy rotation and the definition of dark matter, the part that is invisible to us and is thought to make up about 85% of the universe. Commenting on the complexity of her studies, she once said, "Many mysteries of the universe are still hidden from us. Their discovery awaits the adventurous scientists of the future, and the 9th planet is certainly one of these mysteries." It also remains a mystery to us why, in recent years, it has become customary in astronomical circles to assign newly discovered solar system object names that are absolutely impossible to pronounce, and especially to remember. Why do we say this? Well, do you know what the little goblin was officially named? Lele Konua, which in Hawaiian means something like "fly until the land appears." A very poetic name, but we still miss the days of Pluto, Eris, and Sedna. Now, apart from Lele Konua, we have terrifying names like Oumuamua, Sarojini Naidu, or Sheikh Humar Khan. What do you think? Shouldn't one of the criteria for naming be the ease with which they can be pronounced or remembered?